Hello everyone. We'll discuss some more interesting problems on notches and weirs, and this will be the last class as far as notches and weirs are concerned. Okay, we'll straight away go ahead. So this is about trapezoidal notch. I have chosen the problems from the older question papers, but they will help you in understanding how to deal with, or what is the kind of information that will be given in the question paper, how to interpret and then solve the problem. That is what is to be learnt from these four numerical problems that we are going to do now. Okay, here the actual problem I have not written, but the data is written here. The discharge is 2 meter cube per second when the head is 1.2 meters. It is a trapezoidal notch, that is for sure. And the discharge is 0.6 meter cube when the head is 0.6 meters. CD is given 0.62, and what is asked is what is the length of the crest and what is the theta by 2, or half the angle of the flay that will be given, right? So if we try to draw the figure for trapezoidal notch, it will be something like that. So this is what is L, and then if I draw a vertical, this angle is nothing but theta by 2. This is what is asked. Okay, now we'll straight away solve it. How to write equation for a flow in the trapezoidal notch? It is not Cipolliti notch, right? So you have to put it into parts. That is one rectangular part, one triangular part. Okay, here I have written, and I'll remove this part here. Okay, so total trapezoidal notch discharge is equal to the discharge through rectangular part plus the discharge through triangular part. Correspondingly, I have written the equations also. 2 by 3 CD L root 2 Z H raised to 3 by 2 for this. 8 by 15 CD root 2 Z tan theta by 2 H raised to 5 by 2 for triangular notch. Now if you take common terms outside, you are left with L plus 4 by 5 tan theta by 2 H into H raised to 3 by 2. This is what is the equation. Means the total discharge is given in terms of this. Now if you look at the data, this 2 is given as a total, this H is mentioned as 1.2, CD is given, but you got two unknowns, L and theta by 2, but you got two informations, so it should be possible for you to solve for L and theta. We'll go ahead and do that also. Okay, Q1, the first data, substituting in this, 2 is equal to 2 by 3 CD is 0.62, root 2 G is there, into bracket L plus this is 4 by 5 is 0.8 tan theta by 2, theta we don't know, the H is 1.2 into 1.2 raised to 3 by 2. So this simplifies to L plus 0.96 tan theta by 2 equal to 0.831 if you solve. Now the other data, if I substitute, it will be 0.6, 2 by 3 CD root 2 G, L plus 0.8 tan theta by 2, H is 0.6, 0.6 raised to 3 by 2 is 1.5. So I end up with this equation. Now this minus this, if you do, L cancels off, 0.96 minus 0.48 tan theta by 2 is equal to 0.831 minus 0.705. This gives you theta by 2, means you'll be getting tan theta by 2 value if you take inverse and all. theta by 2 comes out to be 14.69 degrees, right? This value is 3.1 in 3.81, 1 by, right? So this angle theta over here, if I show it in a diagram, you can just see here this angle theta by 2, this it will be 1 over 3.81, means this value is that theta by 2 becomes 14.6. You back substitute this value of theta by 2 in any of these two equations, you will get L equal to 0.579 meters. This is how the problem can be solved. So this is how trapezoidal notch, but they have made it bit roundabout, but it is within the syllabus, and you should be able to flex yourself to these kind of distortions in the problem. It is not straight problem, but one should be able to deal with these kind of things. Next is problem of approach velocity. The problem using approach velocity. Okay, again here also the text or the whole problem is not directly given, but the data is mentioned here. The channel width, you can just see here, the channel width is 0.6 meters. Hope you can understand what I mean. The channel is having a size like that, right? And this corner may be seen there, right? Anyway, you can understand because I have shown these things earlier also. The channel base width is 0.6. The crest of a rectangular notch is 0.4. The depth of the water in the channel is 0.5, whereas the head over the crest is 0.22, that is shown here. Okay, then CD is given to be 0.63. Okay, now you have to find out the discharge, it seems, using approach velocity. Okay, now if I write an equation, Q is equal to 2 by 3 CD L root 2G H raised to 3 by 2. This is plain form in the beginning. We have to start without any approach velocity, just like that, because we have a data for H, data for L, CD, so we have to find out Q, right? So if I write keeping H as it is, this H, so it comes out to be 0.744 H raised to 3 by 2. Now if I substitute for this H as 0.22, I'll get Q1 as 0.0768 meter cube per second. Okay, this is the first one, but we have to include approach velocity. Now we'll calculate what is the approach velocity. That will be nothing but the Q divided by this area. The area is 0.45 by 0.6. that area you have to divide, so that the water moves in the channel with what velocity will be getting. From that you calculate velocity head and then use it for discharge calculation. We'll do that. Okay, Q is equal to A into V. Because of that, the velocity becomes Q divided by the cross-sectional area of the channel flow. So Q is there here, the B is 0.6, this is 0.45 total. Z represents the height of the crust and this is head over the crust, but this total depth directly given as 0.45, that's why H plus Z is written as 0.45. Now if you solve, you get velocity as 0.2843 meter per second. So head, because of velocity head is given by v squared by 2z. Calculating, you get 0.00412 meters, that is 4.122 into 10 raised to minus 3. This we have to include for revised value of discharge. How to do that? Okay, here discharge is given by the same equation 0.744, but instead of plain h, now h plus ha raised to 3 by 2 minus ha raised to 3 by 2. This is the equation for approach velocity, right? If you want to include approach velocity, there is a minus sign here over the rectangular crest. So I will substitute as it is. This h plus ha, I have the values. H is 0.2, ha is 0.00412, total raised to 3 by 2 minus ha raised to 3 by 2. If I solve, I get Q2 as 0.0787, slightly different value from the earlier one. So there is a revised value. Generally this is where we stop, but if you are asked to do the calculations for 2 iterations, we'll have to use this discharge as a discharge coming in, calculate a revised value of velocity, head, redo this calculation, and then see is there any improvement or has it terminated in improvement. We'll do that also. Okay, using this discharge, using the same equation, right? If I calculate velocity of approach, that is VA2, it is 0.2916, earlier was 0.2843. Because of that, I can calculate once again HA, which is VA squared by 2Z. So it comes out to be 0.00434 meters. Now using this in this equation, I'll calculate again revised value of Q. We called it as Q3, same 0.744 H plus HA, this revised value of HA raised to 1.5 minus HA raised to 1.5. Calculate, you get 0.0788, and if you compare, hardly there is any improvement. Because of that, we stop there and then give this as the final value of discharge. So this is how approach velocity works. And what you should remember is this equation, which is plain equation 0.744 h raised to 3 by 2 with all these values, becomes h plus ha raised to 3 by 2 minus h ray. Minus is important, you should remember, for rectangular channels, ha raised to 3 by 2. That's all. Okay, next one. Okay, here the problem is given. It's a broad crested weir, and we have to deal with the velocity of approach here also. It's given like this. Broad crested weir of 50 meters length has 50 centimeter height of water above its crest. Head is given, length is given. Find the maximum discharge. You know that in broad crested weir, whatever equation that we have proved, we have said that the discharge is always maximum, so they need not worry about this particular statement. Find the maximum discharge. Whatever you know about broad crested weir, one equation 1.7 and odd, right? All that equation can be directly used. Take CD as 0.6, neglect velocity of approach. Also, if the velocity of approach is to be taken into consideration, find the maximum discharge when the channel has a cross-sectional area of 50 meters square on the upstream side. So on the upstream side, we have got 50 meters square, right? Channel area. In earlier problem, if you look at, see the upstream cross-sectional area here, it means is 0.6 into 0.45. That is a channel with that depth the flow is occurring. So that information is directly given as 50 meters square. You need not do the multiplication, but directly the area has to be considered as 50 meters square. Okay, with this information, okay, what I have from this problem is, it is a broad crusted weir we have to talk about. The length of the crust is 50 meters, the head over the crust is 0.5, 50 centimeter. Q maximum is asked, CD is 0.6. First part, neglecting velocity of approach. Second part, considering velocity of approach if cross-sectional area is 50 meters square. This is what the problem is. Simple. The first part, equation for broad crested weir for Q max is 1.7 CD L H raised to 3 by 2, if you remember. Otherwise, you revise and then try to know this. Straight away, put everything into the equation, you know all. So you get 18.03 meter cube per second as the discharge. This is first part. Now, knowing this discharge and upper cross-sectional, upstream cross-sectional area, I can calculate velocity of approach. We'll do all that. Okay, here I have written second part. The same discharge divided by 50, I get 0.361 meter per second as the velocity of approach. Head, because of velocity of approach, V squared by 2g, this is 0.00663 meters HA. Now we have to revise Q. So for revision, this equation, how it becomes, just check, is equal to, look at this, 1.7 CDL. This value is equal to 51. That 51 has come here. So only change is h raised to 3 by 2. Instead of that, it is h plus ha raised to 3 by 2. This is what is different. In rectangular channel, we used to do h plus ha raised to 3 by 2 minus ha raised. But here directly the head is revised, h plus ha plus, not minus, right? And raised to 3 by 2. There is no minus term here. Okay. So this gives you 18.39 meter cube per second as the revised value of discharge. Now again, with this discharge, if you calculate velocity, velocity head, and then if you go further, Q revised is equal to 18.406. Now for this earlier first calculation 18 point, revised 18.39, from here it is 18.406. there I think it's fine, but still I have gone ahead with this velocity of approach, head due to velocity of approach, the revised value of Q, it comes exactly the same thing. So it terminates to improve. So we can say that final velocity, final discharge would be 18.406 meter cube per second. This is how. So revision I have done, I think this is the first revision, second, third, 3 revisions of 3 iterations I have done for discharge, and you see that it's almost becoming stagnant as far as improvement is concerned. Okay, next problem. This is in orifice. Okay, a jet of water issuing from an orifice 25 mm in diameter, 2.5 centimeter, under a constant head of 1.5 meter falls 0.915 meter vertically before it strikes the ground at a distance of 2.288. Means the distance x is 2.288, the y is 0.915 horizontally from the vena contracta. The discharge was found to be 102 liter per minute. Calculate the hydraulic coefficients of the orifice. So here CV, coefficient of velocity, is given by, if you remember the equation, it is CV is given by x divided by 2 root YH. Y is the fall of the jet, H is the head over the crust. So as given 0.915, I have made a mistake here, 0.918 I have taken, anyway 0.915, H head over the crust is given as 1.5. Substituting, I get CV as 0.975. This is CV. Now let me calculate Q theoretical here. So cross-sectional area multiplied by velocity theoretical. Theoretical velocity is given by, if you remember, it is root 2GH. Root 2GH. Okay. So I have substituted root 2, G is 9.81 or 981 centimeters if you want in centimeter square, right? 150 is the head, that is 1.5 meters. So pi d squared by is the cross-sectional area of the jet, because 2.5 centimeter is given. So in centimeter cube it will be this much. If you divide by 100 raised to 3, you get 2.663 into 10 raised to minus 3 meter cube per second. So this is theoretical velocity, right? Now Q theoretical is fine, 2.663 liter per second. If you want to talk about liter per second, it is 2.663 liter per second, right? Actual discharge is given 102 liter per minute, right? So I can convert this into liter per second. 102 divided by 60 I have to. So if I do that, I'll be getting 1.7 liter per second. So actual velocity is 1.7 liter per second, whereas theoretical velocity is 2.663. Comparing these two, I can calculate CD. The CD is Q actual by Q theoretical. 1.7 divided by 2.663. If you solve, you get CD as 0.638. I know CD, I know the value of CB. So CD equal to CC into CB, you know this equation from which CC is calculated, and it is 0.655. I think there we'll stop. We'll continue after.